Welcome back from the calculator part of section 6.2. We're going to be looking at more examples, but before we do that, we're going to have a formula. We're going to be looking at the mean or the expected value and standard deviation of a binomial random variable. And the mean value, mu of x, same notation. What we would expect the mean to be would be the amount of trials times the probability of success. That's going to give you the expected value of a binomial experiment. All right, so for instance, if you're doing 100 trials, the probability of success is 70%, you would expect to get 70 successes. So that's where we're looking at for our mean of the binomial random variable. Our standard deviation is the square root of the mean, n times p, times the probability of failure. And then we take the square root of that. Okay, so let's go back to this example. Now the trials are 400, so in a simple random sample of 400 car-owning households, determine the mean and the standard deviation number of car-owning households that will have 3 or more cars. So this is a straight application of our formula. So n is now 400. Probability of success is the same, it's 0.35. So the mean of this particular binomial random variable is 140 households that have 3 or more cars. All right, and then our standard deviation. Again, we plug in our formula. So we could just plug in 140 times the probability of failure, but I'll start from scratch. And 1 minus 0.35, again, is 0.65, so 1 minus p. And we would write that. That bottom stuff ends up being, or the stuff underneath the radican is 91. And then you can approximate that as well. And so we have that the standard deviation is 9.539 households. All right. So we have a way to find the probabilities of our binomial random experiment, and now we can calculate the mean and the standard deviation. Okay, let's go ahead and look at some examples. We're going to examine the shape of some binomial distributions. So here, for all of these examples, our n is 8, the amount of trials is 8, and then what we're going to be varying is the probability of success. So this is the probability of success is 0.15, 0.85, and then 0.5. In this example, this probability distribution, our probability of success is 0.5, so it corresponds to this. And when our probability of success is low and we have a small amount of trials, what kind of shape do we get? Well, if we have a low probability of success, it makes sense that we're going to be looking at values that are smaller, and the majority of the values of our random variable are going to be small because our probability of success is small. So in this case, we get skewed right. All right, and then if our probability of success is half, out of 8 trials, we would expect a lot of those values to be 4. That's the expected value, is 4. And then as we go away from 4, we get smaller and smaller. So this is our bell-shaped symmetric for that p equals 0.5. In similar argument, when it was 0.85, we have a higher probability of success. So we'll see that we get our trials are going to result in a higher number of successes. So in this case, we are skewed left. All right, and then for each of these examples, we had a pretty small n. N is 8. But what we would find And we could run, and we will run some distributions ourselves. When n gets bigger, the binomial distribution becomes bell-shaped. And in general, it's not enough just to say if n's big enough, we'll get bell-shaped. We actually have a rule. This is going on your note card. If you ever want to guarantee or to see if a distribution from a binomial experiment is bell-shaped, it's going to be that stuff underneath the standard deviation. So really this is the variance, np times 1 minus p. If it's greater than or equal to 10, the distribution is approximately bell-shaped. So this is what you guys are checking. Okay, so let's look at an example with that. And this is important for us because if things are bell-shaped, there's a rule we can use. We can use the empirical rule. And the empirical rule can tell us if something is unusual. All right, so let's see that in action. So let's go back to our example. We're going to be going over back to the random sample of 400 cars. All right, so according to Experian Automotive, 35% of car-owning households have 3 or more cars. A researcher believes this percentage is higher than the percentage reported by Experian Automotive. So he thinks it's higher. He conducts a simple random sample of 400 car-owning households and found that 162 had 3 or more cars. Is this result unusual? So this is kind of a precursor of what we're going to be doing for our analysis of our statistics. And we're going to be doing more of this stuff in chapter 8, 9, 10, and 11, our inferential statistics. Okay, so let's get a taste of how this is going to work. Okay, so we already ran this stuff. We know that for 400 households, we just did that on the previous page, mu of x is 140 households. The standard deviation is the square root of 91 households. All right, and then if we verify that np times 1 minus p is greater than or equal to 10, it is. Because this is np times 1 minus p, and 91 is greater than or equal to 10. So we would say that this distribution is approximately bell-shaped. So we can do all these things now with our binomial distribution. We can find the mean and the standard deviation, and we can also tell the size, or excuse me, the shape. And it's approximately bell-shaped. And we're going to use that fact in the empirical rule now, because is this result unusual? Well, we'll see if it has less than a 5% chance of occurring, because we know that's what an unusual event is. Okay? So, let's start making our distribution. So we know it's approximately bell-shaped. In the middle is the mean, which is 140. And we'll start going out, we'll go 2 standard deviations because that will be 95% of the data. So anything outside of that 95% would be unusual, right? Because what's outside the 95% is 5%. All right, so we'll write unusual. And we'll write unusual. Because it's outside the middle 5%. It's in that less than 5%, which makes it unusual. Okay, so that's, again, 2 standard deviations out. Standard deviation is 91. Okay, and then this ends up, if you guys put this in your calculator, this ends up being about 159. All right, so in our example, this researcher thinks that the actual percentage is higher than the percentage reported. And he had 162. And 162 is in that unusual zone. It's in the unusual zone. All right, so it would be considered an unusual event. All right, so let's write that out. All right, so since 162 households is not within the middle 95%, it would be unusual. All right, and why does that matter? It matters because we talked about unusual events before. Either they happen by chance or they happen because something else is going on. So we can write that down. By chance is why that happened, because even though it has a low probability of happening, doesn't mean it's impossible. That's why people win the lottery. But what we're going to assume in our inferential statistics and in this example as well, something else is probably going on. In this case, the researcher was trying to show that the actual percentage is higher than the one reported. And so that's the something else. The researcher can now say, look, I did this sample and it's considered unusual. And I think it's because the actual percentage is higher than the one reported by the Experian Automotive. All right, so we're going to be focused on this one.